right, so now I'm going to talk about comparing prediction models. So two metrics that are often used for comparison are adjusted R-squared and Malocp. And so earlier in this class, we talked about R-squared and we derived it. You also showed its relationship between it and an F statistic in the last lab. And now we're going to talk about something that sort of builds on this, known as adjusted R-squared. So how do we estimate R-squared? Well, it's 1 minus the residual sum of squares divided by the total sum of squares. And how do you interpret this? So R-squared is interpreted as the percent of the variability in Y, so the percent of the variability in your outcome that's explainable by your model. So that's explainable by your X variables or your predictor variables that you've included in your model. And so it's just a fact that adding a new variable to a model can only decrease the residual sum of squares. So I want you to think a little bit about what the residual sum of squares, what that equation contains and why this would be the case. And this is going to be an important question to sort of understand the concept of. But knowing that adding a new variable to a model can only decrease the residual sum of squares, what does that tell us about R-squared? So if this is the equation for R-squared, and if adding a new variable necessarily makes the numerator of this equation go down, and this equation is 1 minus some quantity, where the numerator of that quantity is going to only decrease if we add a new variable, the total sum of squares is going to stay the same when you add a new variable because that's just determined by your Y. And so that means that this quantity overall, because the denominator is going to stay the same and the numerator is going to decrease, then this is going to decrease when we add a new variable. And if you take 1 minus something that's getting smaller as your number of variables is getting bigger, then that means that your R-squared can only increase as your number of predictors increases. And so let me say that again. When you are adding a new variable to a model, your R-squared necessarily increases. And so what does this mean? Well, it means that R-squared as a metric favors bigger models, which is not necessarily what we want to be doing. And so R-squared by itself is really not a good criteria for determining model fit because we're always just going to pick the largest model, even if that change is really incrementally quite small. And so that's where adjusted R-squared comes in. And basically the concept here is, well, what if we could find some kind of scaling metric where we could determine that whether that increase in predictive power is worth it to add that additional variable. So the adjusted R-squared is 1 minus the residual sum of squares divided by n minus p plus 1, divided by the total sum of squares divided by n minus 1. So essentially we're scaling by the degrees of freedom. We're dividing by the degrees of freedom in each of these cases. And so what this lets us do is it basically lets us say, is the increase in R-squared that we would gain from adding one predictor, is it worth it, essentially? So it's only going to choose a larger model. The adjusted R-squared is only going to be bigger if it has some predictive value, if that added variable has some predictive value. So this adjusted R-squared is a better way to sort of compare models because it gives us basically a way to sort of scale these this value such that it takes into account that we're adding a predictor and kind of penalizing us a little bit for that to make sure that adding that predictor is actually really worth it. Okay, Malocp, this is another way that we can sort of compare predictive models. And so this estimates the average mean square error of prediction. And it can be estimated by this equation. You take the residual sum of squares of your smaller model, and you divide it by sigma hat squared from your full model, and then you add 2p minus n. So that sigma hat squared, again, that's that sigma hat squared from the full model, so the larger model that you're comparing to. And the residual sum of squares p, that's the residual sum of squared from a reduced model. And so you would calculate this value for any given model, and you can sort of determine whether or not you can compare this CP value to P. And the reason you're going to compare it to P, or the number of predictors, is because if you set this residual sum of squares P to be the full model and you calculate this value, then you'll end up just getting P, or the number of predictors. And so what I want you to do is I want you to actually show that. I want you to show that Malloc CP for a full model, so where the full model and the reduced model have the same number of predictors P, or where the full model and reduced model are exactly the same, I want you to show that Malloc CP is equal to P in this application exercise.